Hi, I'm Kobus. Today we'll look at a TimeinState application monitoring a gyratory crusher for process as well as equipment. This is the circuit that we'll be looking at. We have the gyratory crusher with the loop system displayed on the screen, as well as on the top left hand side the motor winding temperatures, bearing temperatures, etc. And we will break this particular process into two components, mainly process on the one side and on the other side the equipment. And we will take a modular approach to evaluate and monitor the respective conditions related to this particular crusher. If you take the gyratory crusher and look at production, the production key performance indicators are production rate and utilization. Those are the two components that the production guys will monitor. From equipment point of view, availability is an important aspect, and we will look at the gearbox and motor, as well as the lubrication system as separate items to monitor. When starting a TimeinState implementation, we start by having a workshop with both the production and technical personnel in that particular area that we would like to focus. The first item that we would like to address is to get from the workers their perception of issues and components affecting performance. Now, the first question that we will ask from a process point of view is to say, for instance, what are the key influencing factors causing variable production rate, and on the other end, the variability in utilization. Also, at the same time, we'll look at the equipment and ask the same question, what are the key influencing factors causing equipment availability and the variability of availability on the equipment. The next slide will actually give you a quick preview of the type of information that we captured during those work sessions. We utilize TimeinState and the platform. It's a built-in functionality to capture these key influencing factors. It's a visual interactive session that we execute either via remote connectivity to the plant, where we have a remote workshop facilitated, or then on site. The fact remains that we display the captured information as we go along, and that gives direct feedback to the team as well. Now, if you look at the type of information that we capture, that's listed on the left-hand side in the columns. For instance, around the type of factors that affect the lubrication system. Right at the top, one of the comments from the team was the lubrication oil reservoir level. That was a particular issue when there was a crack in the hull of the crusher, and that became an issue. So that was part of the items listed. It will continue, and the team will all contribute, adding information, their own perceptions during this particular workshop. On the right-hand side, you see a heat map. Now, that heat map, we evaluate and assign values after completing the capturing of all the key influencing factors. And here the team agrees in terms of the impact and probability of each of these events impacting the process and performance. Note, at this point in time, we have not evaluated data at all. We only captured the opinions and the knowledge that exists within the process. It's a very important process because this is where we install the first phase of team learning, aligning the team, making sure that they have all a common understanding of the issues that affect performance. From this, we will go through a process and utilize this information to identify the respective data points that we will use during the analysis, and that is the next step that we will execute. Now this is the same screenshot that we used earlier in this video. With the red dots now identifying the respective measurements that we would like to extract from the process historian to get an understanding of how these different variables interrelate. Now interesting, I may point out at the top the robots. Now those robots are used, it's common on many mines, to indicate to the trucks when they can tip their load into the crusher. Now that signal provides us with very useful information in terms of how frequent those trucks arrive at the crusher. Then on the top left-hand side we have the motor winding temperatures. Those provide us with useful information potentially. And then if we go to the right, there we have our loop system with the flows and the pressures for the respective lines feeding the spider as well as the eccentric bearing, and then all the way to the bottom where we have our reservoir with the pumps, filters, etc. And we will use all this data to understand what are the interrelationships between these variables, identify different operating conditions. And then apart from that, once we've identified the different operating conditions, look at these variables to determine what is our ideal state that we would like to achieve on the respective components. Here we can see the process tags as they are recorded within the process historian. We will ask the site to actually extract this data from the process historian for an interval that we agree on. For instance, to extract data for a 3-month interval, 6-month interval, a year's data, all depending on the application, with a certain sampling rate. On the right-hand side, you can see a typical example of the process data that we extracted. You'll see on the top row, there's your different tags listed. In the left-hand column, there's the different timestamps. In this particular case, the timestamp is at a frequency of 1 minute, so we extracted data from the process historian on a 1-minute interval. This case, we used a 3-month interval to characterize the behavior on these different modules that we will be evaluating for the gyratory crusher. After extracting the data from the process historian, this is where the data is now imported into the TimeinState environment, and we will use it first of all for the analytics. On the right hand side of the screen, you see a typical layout of the maps that we generate. Those maps is they are a visual representation of variable interrelationships. It identifies different operating conditions, and it also illustrates the percentage time that we remain in each of those operating conditions. Now, what we get from this particular analysis, and by the way, we also provide real-time or feedback to the team once we executed the compilation of these process maps. So what we use TimeinState Analytics for is first of all to do data preparation, removing noise, unwanted conditions, extract variable relationships, and then identify the different operating conditions. We previously mentioned that. And one can see that you will remain in a certain operating condition for a certain time and then move to a different. That is valuable information in terms of understanding what the behavior of the process and or equipment is. And then we share this information and observations with the plant workers. And as I mentioned earlier, this is the second stage of that development of experiential learning. These variable interrelationships and the conditions that we visualize within the maps show clearly to the operational workers where they should be operating and where they shouldn't be operating. It contributes significantly to add to their experience, their understanding of how the process and the variable interrelationships work and how the process and equipment act to it. Team learning again takes place because in this particular feedback session we have again production on the one side as well as maintenance, the technical team, and this interaction between the different teams while providing this feedback, this is where the team learning takes place. And using data from the plant means that we clearly illustrate to everyone present exactly where the plant is actually operating. So this is part of that change management process and aligning both teams and all the individuals in that particular workshop to a common understanding of the issues affecting the process. And then more important also is the systemic thinking, holistically thinking about the process, because the crusher is not only the function of breaking ore down to a smaller size. It is a combination of electrical, your motors, mechanical, the gearbox, the lubrication system, which is also a mechanical function. Now, all of those systems work together in order to deliver certain output. And one has to have this holistic view of this complete process to understand what defines that optimum operating envelope, which is the next step that we execute. And then we take the definition of this optimum operating envelope and we deploy a model that now will do real-time interpretation of the operating conditions that we will illustrate in the next few slides. Here we see an illustration of the respective models that we deployed for production and equipment monitoring. On the left-hand side, we're monitoring production rate, and we look at the tip rate, in other words, a rate at which trucks deliver material to the crusher. There is your feed rate from the rock box as well as your crusher power, because all of that tells us about the production components of the primary crusher. Clearly, the primary crusher from a process point of view is not a complex process, and therefore it's a very simplistic model monitoring production, but providing useful information. And on the next slide, we will also look at the different benefits that that particular model actually delivers. On the equipment side, there obviously we would like to monitor the lubrication system and understand what is causing a deviation from an ideal state. Now on the top, you can see that the dial moved outside of that optimum operating envelope, the green area. And then you will also see that there's only one bar colored red at the moment, because that is the particular variable causing that particular module to be outside of its optimum operating envelope. Then at the bottom, we're monitoring the crusher motor. It monitors the various components and then provides us with a real-time indication of how well that particular electrical motor is complying to its optimum operating envelope, where that optimum operating envelope was defined and developed by the team during the previous workshops that we illustrated. We will now illustrate a quick live demonstration of how we do the monitoring. On the screen you will see the web page. It's a web application that you log into, and this gives you access to your particular application monitoring your plant. So whether you're on site or off site, you have availability and visibility of this particular monitoring solution. After logging in, this is the one screen that you'll see in terms of the different operating or modules that we're monitoring on the particular process. In this case, we will look at a particular process, and we are interested in this particular primary crusher loop 2 module, monitoring the conditions on the lubrication system of the gyratory crusher. So by clicking on it, we open this particular screen that shows us the real-time view of the operating conditions on the gyratory crusher loop system. So here we can see we're right on the edge of that so-called optimum operating envelope. We notice that the one variable causing us to be below that target variable or target condition, the optimum operating envelope, is our reservoir level. This is clearly illustrated here on the right hand side. If you can maybe just to highlight that, that is the area, and that's our reservoir level, showing that it's below its ideal state. It's not at a low level where there's an alarm condition on the control system. This acts as an early warning of that particular condition. We also have relevant messages that one can display. You can customize those messages that one can share that with the particular process. And there we can see we move just back into that ideal state. So we're right on that edge of the ideal state where everything now turned green. This line graph here at the bottom gives us about a 40-minute historical view of this dial's position. So if you look at this particular dial, that needle position, that blue line is the historical view of its exact location within the dial. We have two levels here, L1 and L2. L1 is the position right here, that borderline there, and L2 is that borderline condition right there. So one can see how your dial position then moved over the 40-minute historical view during this interval. Now, what are the benefits that we realized by implementing this particular TimeinState solution on the gyro crusher? First of all, from the production point of view, the deviation from the optimum operating envelope provides an early warning of issues causing a drop in material feed to the plant. This information assists the operational manager or process engineer to act on the root cause. You know, why is there a deviation or lower production output? In this particular application, the primary crusher processed two different types of ore type A and B, where A is only processed on plant A, and the ore type B is only processed on plant B. So these stockpiles are fed separately. And understanding the issue at the crusher can be evaluated in the context of the downstream stockpile levels. And it may prompt a change in ore type, a switch from A to B in terms of feed, or vice versa, all depending on the circumstances, and that at least sustain the production rate from the primary crusher. From an equipment point of view, the purpose is really to monitor and provide early warning of deteriorating performance on any of these components that we are monitoring. The type of benefits that we realized is, for instance, early warning of a particular failure on the electrical motor. That was identified in advance, early enough for the guys to come out and do detailed analysis of the issues causing that deviation from the optimum operating envelope. That also provided sufficient time for the technical team to bring the electrical motor, 5 megawatt motor, from the store down to the crusher installation. If this didn't take place in advance, it was quite possible that this particular plant would have suffered at least a 24-hour downtime interval. From a lubrication system point of view, we successfully used this particular application, the two different modules, where the one monitors the electrical motor and the other one the eccentric bearing and the lubrication system, where we detected foreign material passing through the crusher, which then subsequently damaged the eccentric bearing. But that early warning gave information that allowed the guys to take certain actions to extend the life of that eccentric bearing, obviously with that eccentric bearing replaced later on. Overall, these actions delivered a higher production rate from the primary crusher.